What's up, physics gang? So, to wrap up our recap of frictional forces and Newton's three laws of motion, we're going to go to probably the trickiest part of this study, but it's really not that bad once you just kind of get the hang of it. So, what we're going to go from is something on a flat surface to the forces, including weight and friction, but on a inclined plane, which means on a tilt, right? You're on a surface at a certain angle. Now, this looks like gobbledygook, but really quick, just remember that if something's on a flat horizontal surface, right, we have the applied force, friction is the other way, weight points down, and normal force points back the opposite way of weight. And if we go to the reference tables, we know that if you were to pull something, like let's say with your arm at an angle, right? If you're pulling something at an angle, to find out how much the force would apply in the x direction, we would use cosine. And to find out how much the force would pull in the y direction, right, vertically, we would use sine. But when we're on an inclined surface, which means, again, at an angle or tilt, right, in inclined plane, the trigonometry gets reversed. So let's just try to see what's going on here. So we have an object on a surface that's at an angle. Yes, gravity is still pulling straight down. You see where it says Fg? But the thing is, because gravity is pulling straight down, but this object is on a surface that is at a tilt, what we have to do is we have to break the gravity, the weight, right? The force from gravity, the weight, into two components. So basically, we have to resolve it into two components. So break it into two components. So we have the weight of this object is pressing onto the surface of whatever it's sitting on. And for that, now we're going to be using cosine, right? So normally when something's on a flat surface, we don't have to do any trigonometry. It's just the weight, right? Mass times gravity, done. But on an inclined surface, to find out how much this object is weighing down on the surface, we must use cosine. And then, of course, as we know, right, anytime you've stood on a hill, you could trip and roll or slide down. And that's because gravity is pulling you to the side as well, right? So it's pulling you onto the surface, but it's also pulling you to the side. Now, to find out how much the weight is pulling to the side, we must use sine. Why this happens is really just geometry and trigonometry, right? So if you have a right triangle, but you start to complete the shape. So basically, we start just turning it into a rectangle. We notice that this original angle with the Greek letter theta is equal to this angle. And then when we do the trigonometry over here, it turns out that if you find this leg with the yellow arrow, you end up needing to use cosine. Now, if you follow over back to our object, this box sitting on the incline, oh shoot, look at the yellow arrow that's pointing that way. That's going to be equivalent to this arrow, and then therefore we must also use cosine for that arrow, for that vector, I should be saying, right? What about this vector with the orange arrow pointing this way? Is there another vector on the object that's pointing the same way? Yes, there is. And now, if you notice, because we completed the shape and we saw that to find this vector pointing, I guess, down into the side, we must use sine. Well, then we must use sine for that also. So here's another way to look at it, right? When something is on a level surface, whatever amount of force, so A stands for whatever, cosine of theta will give the x component, and a sine of theta will give the y component. If something's not being pulled at an angle, we don't have to worry about it. But on an inclined surface, again, because of the way the geometry works out, to find out how much the object is weighing onto the surface, we're going to end up using, in this case, this purple vector, which is cosine, which, by the way, also gives us the normal force, right? Because normal force must be pointing up perpendicularly from the surface. That's literally what normal force means. Normal means right angle. And then to find out how much the weight is pulling down the incline, we must use sine. Okay, so that's really it. So why don't we try to do a question with an object on an incline and solve for the forces, and then hopefully it makes more sense. So let me grab, I don't know, use a different color this time. Okay, so this is going to be a recap of forces on an inclined plane or surface. A plane just means a flat surface. Okay, so how's about this? One thing that I want to keep going as we're going along with the question, we should be trying to look at a free body diagram. So I'm going to do my best. Obviously, you see that I cannot draw very well. Oof, that's quite a sharp angle. Let me try one more time. It's a little sharper of an angle than I wanted, steeper of an angle. Whatever. Something like this. I don't care. All right, so this is going to be our free body diagram. So now I will draw the object. Oops. So I don't know, I guess I'll say that the object is chilling right here. It doesn't matter if it's a box or not. Okay. And now we can actually start, before we do any math, we can start labeling the forces on here. So we know that gravity itself is just going to be pulling straight down, right? So that's Fg. But the thing is, gravity is also going to pull down this way. So that's also gravity. And then gravity is also pulling the box directly onto the surface. So that's also gravity. We know that because the box or whatever object it is pushing onto the surface with its weight, that means that the surface is also going to push straight back up, which is going to be the normal force. And then we also know that since the object is touching the surface, that there's also going to be friction trying to stop the sliding down the hill from happening. And also, we're going to have to figure out what that angle is. Okay, so now that we have a free body diagram that we're going to start filling in as we go, let's get cracking. So let's see, let's make up a couple of things here. So there's our free body diagram. Let's give this object a mass. Let's go with a nice, cool 150 kilograms, something easy. 150 kilogram object. Don't forget, we always have gravity, so 9.81 meters per second squared. And then we need an angle. So let's say that the angle, Greek letter theta, is equal to, I don't know, let's just go with something easy, 25-degree angle, something like that. Is my picture at 25-degree angle? Probably not. Doesn't look that bad, but whatever. Okay. So we want to determine all the forces acting on this object. If we want to make it even more complicated, which I think we should since I'm helping you along with this one, is why don't we figure out what these surfaces that are in contact are made out of so that we can practice doing coefficients of friction as well. Maybe, let's say that it's copper on a steel surface. Sure, why not? Right, we haven't used that one. So this is a copper object on top of a steel, which is basically iron, surface. Okay. All right, I think we have enough info to go. So here again, don't panic. This is where you always want to start off. Always start, step one, always get the weight. Again, excuse my terrible handwriting. Writing on a computer screen is not making that any better. So we want to get the weight of the object. Now we're going to get weight the same way that we always do, by using the equation for gravity, but cross-multiplying it. So here, let's go to that. So, or I shouldn't say gravity, it's gravitational field strength. But remember this equation right here, G equals Fg over m. Remember, Fg is weight. So if we just do gravity times mass, we get weight. Okay, so easy peasy. Let's do it. Weight is mass times gravity. All right, let's plug in. So what do we have? 150 kilograms multiplied by 9.81 meters per second squared. All right. Calculator time. 150 times 9.81. 1471.5. I'll just go with a nice cool, let's round it to a whole number. I don't really care about significant figures in this current situation. We should care, but I want us to focus on how to solve this. So let's go with 1472 newtons. Was that correct? Let me double check that. If we round it. Oh, hey, what happened? Come back. Yeah, 1472 newtons. You know what? I might want that to stay there while we're working on this. Okay, so now we have the weight. Now here's the deal though. What we just got is the weight if it was on flat ground. So now what we have to do is find the parallel, which means along with the surface, and then the perpendicular. So why don't we find the weight parallel to the surface? And if you're not sure what that is, that's this guy. All right, parallel, remember, that means that lines will never intersect because they have the same slope. So whatever's going along with the slope is parallel. Okay, so now let's go back to the notes though. What do we use to solve for parallel? Sine. So we're going to use sine of the angle. So we're going to take the weight. So it's going to be the weight times sine of the angle. That's how we get the force pulling, the weight pulling down the hill. Okay. So it's going to be 1472 newtons. Sine of, we said the angle is 25 degrees. All right. So 25, where's my trig on this thing? Oh, this one actually lets me write a complete sentence. Okay. Yeah, some calculators are different. This one apparently lets me write out a full mathematical sentence here. So 1472 sine of 25. 622, that's it, 622. 622 newtons. So I'll be honest with you, once you get the regular weight, honestly, when you're on an incline, I don't even care about that. I care more about this. So I'm going to start labeling these. So I care about these four. So now we know that what? The weight pulling parallel to the surface, meaning pulling down the hill, is 622. So I'm going to make a note of that. This is 622 newtons. Okay, cool. Now let's find this weight, which is perpendicular, right? Meaning going to make a T. So this is the perpendicular weight. So let's find that. So this is going to be perpendicular, which the symbol is this, right? So basically at a right angle. So now that, let's double check the notes. The perpendicular force pulling, the weight basically pulling onto the surface, we must use cosine. So it's the weight times cosine of the angle. So this is the weight times cosine of the angle. So that's 1472 newtons cosine of 25 degrees. All right, let's do that. 1472 cosine of 25. 1,334 newtons of force. Okay, and now I can label that. This is 1334. 1334. All right, now that we did those two things, everything's going to become quite a bit easier. All right, so now that we know that the weight pushing onto the surface is 1,334 newtons, what that means is we now also know the normal force, because normal force is equal to how hard the object is pushing onto the surface. So this is also going to be 1334 newtons. That's how hard the floor is pushing back up. And wait a second, now that we know normal force, we can solve for friction, right? Because friction is the coefficient of friction times the normal force. Okay, sweet. So now what we can do is figure out what the friction level is, and we can determine if the object will slide down the hill, whether it will accelerate down the hill, slide with constant velocity, or whether it's just stuck because the friction is so strong. All right, so while we're here, why don't we write down the friction equation. So step 2. So we got the weight taken care of. Now we can finally calculate the friction. And then we could figure out what's going on in this situation. So the equation for friction is coefficient of friction times normal force. All right, so first, why don't we calculate the static friction? And then if the object is sliding, we'll get the kinetic friction. All right, so static friction is frictional force, but we need to now look up the coefficient of static friction with a copper object sliding on steel, or not sliding on steel. Maybe it's sliding, maybe it's not, just in contact, touching. All right, copper on steel static is 0.53, okay? So that means we're going to take 0.53 and multiply that by the normal force. And don't forget, the normal force is how much the weight, it's equivalent to how much the weight is pushing onto the surface but pointing back up. So once you find the perpendicular weight, you found the normal force. So it's 1334. Okay. 1334. Oh wait, I don't need to do any trig. It's just times 0.53. 707 newtons. 707 newtons. Okay. And what about if the object is sliding? Let's just go for it. Might as well. If the object is sliding, the force of friction will be, now, if this copper item is sliding on the steel, then the friction will be the coefficient of friction will be 0.36. So if it's sliding, that will be 0.36 times the normal force, which is the same as the weight that is pushing onto the surface, the perpendicular weight. All right. 0.36 times 1334. 480. All right. Now we have all our data and we can just analyze this. The static friction is 707 newtons. If this amount of friction is not overcome, right? Remember, if static friction is not beaten, then the object will not be able to start sliding. If it's sliding, then the friction will be 480, right? I thought I made this much thicker. Yeah. Oops. Sorry. I was like, I could have swore that I made that. Yeah, there we go. So let's see. Is the weight, the force pulling down the hill strong enough to beat the static friction? So basically, we can think about it as checking this. If the friction is 707 newtons, will it be overcome by the weight pulling down the hill? And no, right? Because 622 is not equal to or stronger or higher than, right? It's not equal to or greater than 707. Therefore, if we just look at the object as is right now, it will remain still. And there we go. We can come to a conclusion about this physical situation here. The static friction is 707 newtons, which is greater than the weight parallel to the surface, which I'll make a note of is, what is it? Just make a note, 622 newtons. So 622 newtons. Therefore, the object will remain at rest. There we go. So if static friction is not overcome by another force, the object won't move yet. It's stuck. Will remain at rest. And there we go. If the weight pulling parallel was greater than 707, then the object would start to slide down the hill. But that's not the situation here. All right. I think that's enough. I hope that this helped you understand how to calculate the forces acting on something when it's on a tilt, which is an inclined plane. Oh, and cool. The Google Doodle for today is about the Enya. Time to put on my Puerto Rican hat. Later.